Here now I am showing the summary and the tree structure, basically a flow chart about the strong consistency and high availability, and then later on I will explain each of those things in detail, that how in this fintech system design, how we will balance the strong consistency and high availability. We will divide all of the operations between the operations which are supposed to be highly consistent and the operations which need to be eventually consistent. So this restructure will help us in properly getting the idea that if there is any operation, any API call, any request from the client side, or then how the backend microservices will decide that where they need to go through for this call. If the operation will be strongly consistent, uh, we can divide these all operations into some schema, into some along with their IDs. There will be some parent table which can decide that, and in that database table, we will also make sure that like there can be some table present, we can name this table as operations, and this will have an ID, column name ID, and then operation name, and then operation name, and then we will have a type ID, and then there will be another table of operation types. It will have an ID and type, and what will be the data in this table. These two, this will be table parent table with only these two columns here. So what will is the normal data here in this operation types table will be, it will be having these values: strong consistent, actually consistent, and then will be something like that. Wait, the strong consistent, and then basically all of these different types it can have, and then lead sync eventually consistent, sync eventually consistent, and then this will be the white sync eventually strong consistent, and then read async strong consistent, and then white async eventually consistent. 4 types here, and then 4 will go here as well. In case of let me just copy these. Paste it here. And then now I simply move, need to update strong with the eventual. So that's how it will be. These operation types will have these 8 rows present, and now based on these 8 rows, all of the operations will have these type IDs present, that what will be the all operation types present here. Based on these, backend microservices will decide that from where they need to, that how they need to complete this request. So if there will be strong consistent sync read, then they need to go to the read from secondary DB server, or they need to write to the primary DB server directly, or they need to read from secondary DB server via Redis, or they need to write to primary DB server via Apache Kafka. So these will be 4 approaches that how they will, backend microservices will decide. And here we can see that all of the backend microservices are being connected to our Redis cluster, and also to our Apache Kafka cluster directly and indirectly as well. And similarly, all of the backend microservices are being connected to our secondary SQL DB servers and all of the RAID replicas as well. And we are also replicating data from a primary to a secondary SQL DB server via Apache Kafka, because the primary and secondary SQL DB servers will be present in different availability zones. So it doesn't make sense to synchronously copy replicate data from one SQL server to another. So it should be an asynchronous approach to properly prioritize the high availability thing. So that's how it will be. That's how we will keep both strong consistency and high availability in balance with each other. Strong consistency and high availability in balance with each other. Hi, so yeah, let's move on this series further. And let's discuss how we will balance strong consistency versus high availability in this system diagram case study about the fintech. As we remember that the main functional requirement, non-functional requirement was the high availability, but we still don't need to forget that we are developing the banking platform, and in the banking platform, data is very important. So we need our system to be consistent as well. So what we have figured out is that we need to draw some balance between strong consistency versus high availability. So some of the actions like transfer money, withdraw amount, deposit, update ledger, and approve high value transaction, eventual consistent more available. These all operations will be strongly consistent, and then we have some other operations on which we can compromise. And how will we compromise? These will be highly available operations. Like we have old statement history, notifications, analytics, search, and profile grids. These will be highly available at all time. Here we also need to make sure that let me also update that notifications async notifications is async highly available. So there is a minor difference between these two, and also same goes with the search is sync highly available. Like if user is doing some search, it is synchronous operation. At the same time, when user is doing some searching, it is waiting for the search result. So it is that why it is a synchronous operation. But the notifications are asynchronous operations decided by the server and sent via notification service via push notifications. So at that time, user specific is not waiting for the notifications to be received. But search is a synchronous operation. We need to be properly differentiate between these two as well. But the main point what I am discussing right now is the difference between strong consistency and high availability here. That these operations, these requests will be highly available. And same goes with the profile grids. In some cases, this will also be a synchronous highly available, and dashboard data will also be a synchronous highly available. Okay, let's move to the structure in the database. Here I will explain that how, like we have this primary SQL database server present here, and primary SQL database server, and then this will be available in one region, and then the secondary SQL server will be available in some other availability zone region. So because the region difference, so we cannot replicate data from these two database servers synchronously within each other. So that will increase the latency of the system. So that's why how we are replicating the data between primary SQL server and secondary SQL server is via messaging queue like Apache Kafka between them. So as we will be using Postgres SQL server, so we will be using the WAL write ahead log replication between primary SQL server and a secondary SQL server. So in this case, we will properly make sure that if one of the primary or the secondary, and then we have some other read replicas present as well. So this whole architecture makes sure that our system is both strong, consistent, and highly available. And how it is, like if a primary SQL server goes down, then via leader follower election mechanism, we will make sure that all of these other nodes, these nodes, and this is also a node, these nodes will do an election between them, and they will make sure that this one of those most probably this will be the secondary replica server. This will become the leader in this case. So That is the scenario. The data movement between the primary and secondary will be done whenever there will be any request from any of these backend microservices. Then first of all, primary SQL database server will make sure that secondary SQL server has also that same data being replicated. And when the data will be replicated, then SQL server will send the success response to back to the backend microservices. If the secondary SQL server has not that data written yet, then primary SQL server will not return the response back. So that is to properly make sure that transactions are properly being copied and there is not any data loss between primary SQL server and the secondary SQL server. So that is the reason. So that is how we will achieve the strong, consistent approach here. So before that, here we saw that there some of the operations were strongly consistent and some of the operations were highly available. So how we will achieve this? Backend microservices, their logic will be properly implemented at the backend microservices codes here. So if the operation will be highly available, then backend microservices will first request those that data from the Redis cluster, Redis session store, and backend microservices will not directly query those requests from the database servers. First, it will request from the Redis cluster, and if the data is being received from the Redis cluster, then it will be returned directly from there. And if the data is not present in the Redis cluster, then first of all, backend microservices will request those from the primary SQL database server, and after getting that data from there, it will these backend microservices will make sure that though they write that data into Redis cluster as well. So that's the approach will be used, and same goes with the synchronous and asynchronous. If that operation will be asynchronous, then backend microservices will go will demand those requests from the Apache Kafka and not directly from the primary. And if they will be synchronous, then backend microservices will directly communicate with the primary SQL database server. So that's how backend microservices will communicate from primary SQL DB server, and also that how they will approach the highly availability thing by first getting those values from the Redis cluster, and if not available there, then asking the primary SQL DB server to get the data, and then they will write also to Redis cluster as well. And same goes with that how primary, whenever there will be any write on the primary SQL server, that write will be immediately replicated to secondary SQL server, and from the secondary SQL server via Apache Kafka, those all data will be also be replicated to all the read replicas as well. So whenever there will be any read query, all the backend microservices will request to the read replicas and not to the secondary SQL server. So that's how the differentiation will be. And in the next video, I will try to make a proper flow chart for this.